Hello, Ian here, Victor Kilo 7, India Alpha, November. I just thought I'd run through a couple of points that I think might be of interest. And I'll start with the simulating the FPGA code. So you can see here I'm in the directory where the digital down converter files live in the simulation directory. See, I've done a few versions here. But basically I've started a PowerShell and gone into Windows Services for Linux, where the Verilog simulation files live. And I'm not trying, this is not meant to be a tutorial, but I just wanted to demonstrate how you can simulate the FPGA while you're developing the code. So it's actually, once you've set everything up, it's actually fairly straightforward. And you run this iVerilog process that generates a simulation file here. And it's actually fairly quick. The simulation file gets generated, and then you process the simulation file through what's called a test bench. And the test bench is basically Verilog that exercises or calls the modules. So what I've set up here is an input signal of 1500 hertz over 10 megahertz, so 10.0015 megahertz. Sample rate is 80 megahertz, and the tuning center frequency I've set it to, sorry if I can get there, simulation clock here, sorry, at 10.001 megahertz. So with the tuning clock, the numeric clock oscillator set to 10.001 megahertz, and the input signal set to 10.0015 megahertz, we should see a 500 hertz difference. Two outputs at 90 degrees phase shift. So we're just going to run that simulation now and generate this file ddc1.csv. There we go. And now we can open up that file. Yeah, there we go, ddc1.csv. Right, now what I want to do is plot these values. I'll just get rid of this notification here because it stuffs up the plot. Alrighty. So we want to insert a chart here. And there we go, look at that. To a quadrature signal, very clean. Now, let's just double check the frequency. We have a point here at 82 and a point here at 145. So 145 minus 82. Now these steps are at the output frequency of 31 kilohertz. So it's 32 microseconds between steps here. So we divide this by 31250 and take the inverse, 496. So we've got our 500 hertz signal at the output, nice clean sine wave, amplitude of 5,000 or so. So that's just a quick demonstration of how you can simulate your FPGA program. The other thing I wanted to show you was the GoWin simulation report, the timing analysis report. So this is where you actually build the GoWin IDEs, where you build the build and synthesize your Verilog code for the FPGA you're interested in. But I won't demonstrate that. It's just a matter of writing building your project, writing your code, running the steps to generate your bit stream file. But I just wanted to show you the timing and analysis report here. If I can make this a bit bigger. Just want to show you there's a lot of information here, but this particular parameter here, the constraint is we want to run at 80 megahertz, but the actual frequency it could run at is about 93. So what that means is we're in good shape. But I can tell you this is purely luck on my part. The GoWin board that I found, this board from Brisbane Silicon. A bit hard to see there because of the backlight. Hang on a tick. You see that a bit better now. Yeah, the GoWin board, development board from Brisbane Silicon. It's purely luck, basically, that it worked up to 80 megahertz with this 10% margin. So I'm very, very pleased that that's worked out well. The next thing I thought I'd have a look at is the circuit diagram. And you can see the block diagram here, which I showed last time. And basically the circuit just follows this almost exactly. Not sure how well that comes up. Well, pretty well. So if you follow the receive path, the signal comes through the SWR detection here, through the low pass filters, down through this TXRX relay here. It's a read relay. Really like read relays, they operate silently and within 2 milliseconds. Then I've got a 12 dB attenuator here through some large signal suppression protection, and now I've got some switchable high pass filters here. So this is the bias for the switching IC, and the low pass filter combined with the high pass filter. You can cascade them and it works out quite well for a band pass filter. And into another switching IC and into this is 20 dB of gain, and the bias for the switch is, this is DC coupled to the switch to give the switch the bias it needs, and that's just fortuitous. The input to the MMIC is around 2.5 volts, which is perfect for biasing the filter switch. The output from the MMIC goes to the to a single-ended to differential transformer here. It's a trifilar transformer. So what we get here is, because this is trifilar, you get basically 6 dB of free gain. Now, why do we have this resistor here, this 50 ohm resistor? Well, the 50 ohm resistor provides the correct load to the MMIC and therefore to the filters. But the input here to the 89236, the inputs here are high impedance. They're around 100k ohms impedance, input impedance each. It's a voltage device, not a current device. And so basically the data sheet recommends that you use this small filter arrangement here. Now, the 50 ohm resistors here, I just chose those so that you get a reasonable cutoff above 30 megahertz, and also means that the BOM, it reduces the variance in resistors in the BOM. So this trifilar also means you can bias the input to half the supply rail. All of the capacitors here are basically from the data sheet. Nothing special there. And the output from the ADC goes into the Brisbane Silicon GoWin FPGA and into these pins here, these 12 pins here, and the other pins we need from the FPGA, well, we need to clock the ADC and a DAC with 80 megahertz. So there is a the FPGA development board from Brisbane Silicon comes with a 27 megahertz clock. Now, 27 megahertz doesn't give you 80 megahertz with any division of the phase lock loop. So what I've done is I replaced the 27 megahertz clock on the development board with a 24 megahertz TCXO clock. So that means two things. You can derive your 80 megahertz precisely, and it's a TCXO, so it's not going to drift. It is possible to run, or it's an FPGA, so you can get it to generate an 81 megahertz clock, and then we change the divisor so that instead of decimating by 2560, you decimate by something else. I forget what it is. But in the meantime, I'm using TCXO at 24 megahertz. The other interface pins here, so the tuning, there's a SPI interface for the tuning word, so the chip select, the clock and the data, and we've got a SPI interface for the IQ data, so a chip select, a clock, and an input and an output. Those pins all connect to the Pico here. And when we have the audio. So the audio is generated from dual pulse width modulated pins from the microcontroller. It's the same as the phasing transceiver, and the microphone input biasing for the electret microphone, a single op amp amplifier straight into the ADC of the microcontroller. This is the LCD, main tuning encoder, and the paddle inputs, headphone output, and the relay control is here. It's an I2C relay control. That's basically the receive path. The transmit path obviously starts with the microphone here. The microcontroller generates IQ transmit at baseband, sends that to the FPGA, which does the up conversion to the frequency you want to transmit on. And that is output on the 10 pins for the DAC, digital analog converter. Here is clocked at 80 megahertz. This is directly from the data sheet, the AD9740. 10 bits input, and we have a current output. So this resistor here sets the maximum current. And so we need now to go to the filter, the image filter for the transmit, which is up here. So the whole transmit section amplifier is this. So we have the filter here. So this is a current output. So that means you can set the impedance just with the resistor. So the resistor here is a 50 ohm resistor, a 50 ohm filter, and the op amp, the OPA 2674, is a high speed, wideband, high current output op amp. Which means, and we're driving the negative input. So this 50 ohm resistor provides the 50 ohm needed by the filter, and has a gain, what's that gain? 50, gain of 5 here, sorry, 10, a gain of around 10. That drives the MOSFETs here, which is just a differential to single-ended transformer output into the filters, the switched filters, and then through the SWR detector, which is the same one as I use for the multiband phasing transceiver. Just a couple of 10-bit I2C analog to digital converters. So you can see that with the FPGA and the DAC-ADC arrangement, the analog section is essentially 70% filters and 20% simplified analog amplifier, and there you have it. Now, I've designed the printed circuit board, revision 1, and I'm not going to go through it all. I do follow some strict rules when I design a board. Always at least 4 layers. Inner layers are ground plane. Plenty of stitching vias and a ground via for each device that's connected to ground itself. But I just wanted to look at the filter building filters on printed circuit boards, and I've seen two kind of methods for doing this. One method leaves the top layer ground plane intact, and another method removes the top ground plane. So what I wanted to find out is what difference it makes. So I created some test boards with ground plane on the top for one filter and no ground plane for another filter, same filter, and just to see and measure what difference it makes. So I've got the nano VNA connected to the bottom filter with no ground plane, and you can see here the frequency response. Very nice actually response here, 70 dB down and heading downwards. But I'll just switch over to the other filter with the ground plane and see what difference it makes. These connectors are tricky. Okay, there we go. Well, pretty much identical essentially. So from the point of view of building these filters or designing the board for these filters, I'm not going to worry about removing the ground plane. That's basically all I wanted to talk about today. And I hope that was reasonably interesting. And we'll see you in the next video. Hopefully we'll have something built up, ready to go. So thanks for watching. This is Victor Kilo 7, India Alpha November. Take care.